All right, so one cool thing we can do with nitriles is they can be precursors for carboxylic acid. So if we want to add a carboxylic acid in some place, we can first add a nitrile group. And remember our cyanide, we did a whole bunch of different reactions with there, mostly the vast majority which are just SN2 reactions. It's a good nucleophile and it's a weak base. So they generally do SN2 reactions. We don't have to worry too much about E2 reactions. So for example, you can have a secondary alkyl halide, and if you add some cyanide to it, usually sodium cyanide, it'll just do an SN2 reaction. But it is an SN2 reaction, so primary and secondary, okay. Tertiary, no good, right? Even though it's a weak base, it still can't do tertiary SN2 reactions. After this, we have some options. You can just react it with some hot acidic water, and then it'll transform into a carboxylic acid, right? So this carbon right here ends up being this carbon right here. Let's go ahead and take a quick look at this mechanism. It's a lot of proton transfers, but it's not really too bad. So we've got our nitrile. We're in acidic solution. So remember, we generally want to avoid negative charges in acidic solution. So the first thing we're going to do is we're going to take that lone pair, pick up this H+. Now we've got a positively charged nitrogen, which makes our carbon more electrophilic. So what we can do is we can take a water molecule, right? Water, not hydroxide, because we're in acidic solution. And then we can attack this carbon and then kick off one of the pi bonds onto the nitrogen. After this, we can have a proton transfer occur just so we don't have water. After this step, we have essentially what's just another proton transfer. We have a water molecule come pick up this hydrogen and then transform this OH bond into a carbon oxygen bond. So we're going to form our kind of carbonyl here. And then, of course, we have to kick off this nitrogen carbon bond, and we'll just have that pick up an H+ to keep things neutral or positive. Because again, we're in acidic conditions, so we want to avoid any negative charges. And so then we stop here. We're at an amide. From what I've read, you can't really stop here, though. The reaction is going to keep going to a carboxylic acid. So at this point, we kind of somewhat repeat the process. We have H+ floating around. So let's go ahead and just have our carbonyl pick up an H+. Make it more electrophilic. And now we have our electrophilic carbon down there. We can take another molecule of water and go ahead and attack our carbonyl and destroy our pi bond. Now we've got this compound right here. We can mix around our protons to do some proton transfers. Again, stay away from negative charges because we're in acidic solution. We're going to protonate our nitrogen. That's the most basic component. And also that's what we're going to have be our leaving group. So we're just going to have a lone pair from one of the oxygens form a carbonyl. And at the same time, we're going to kick off this amine, right? This NH3+. Now that's protonated makes for a pretty good leaving group. Then what we're left with is our protonated carboxylic acid and of course NH3 floating around. Then we just do one final proton transfer to make our carboxylic acid neutral. So pretty long mechanism there, but overall it's pretty intuitive, right? We can also do this in basic solution. Can also do this in basic solution. So if we have a cyano group, you can just add some sodium hydroxide. And then you do need to do an acidic workup just to reprotonate your carboxylic acid, but you end up with a carboxylic acid. Check out the work along for this mechanism. Overall, again, it's pretty consistent with what we've been talking about. In this case, we have a base, so we want to avoid positive charges here, and negative charges will be more okay.